Well, welcome everybody to HydroTerra's latest webinar. This is the first time we've done a sequel, and it's exciting to have Mark Stuckey back for part 2 of an auditor's perspective, undertaking Tier 2 and 3 assessments under the ASC NEPM framework. Mark Stuckey's a Senior Principal and Contaminated Land Auditor with Environmental and Earth Sciences, and we're lucky to have him here today to present on this topic. Before I move to the next slides, just to recap, you'll remember Mark presented on this topic, but the focus was more on soil side of things. This picks up where we left off, but we do a bit of a recap to set the context in a few slides at the beginning and then move on to water side of things. Before we get started, I would like to begin by acknowledging that we conduct our work across this great land, and for that privilege we would like to thank the traditional owners. HydroTerra respectfully acknowledges the Boonwurrung people of the Kulin Nation where we are located today. We pay our respects to their elders, past, present and emerging. There's a picture of our presenters. A little bit about our presenter. So Mark Stuckey is a Senior Principal Soil Scientist. He's a hydrogeologist and a risk assessor with over 30 years professional experience specialising in the investigation, remediation and management of sites in Australia, New Zealand, Southeast Asia and the United Kingdom. He's an accredited contaminated land auditor in New South Wales, Victoria, Queensland and the Northern Territory, a certified professional soil scientist accredited in contaminated site assessment and management, and a registered soil practitioner in acid sulfate soil. Mark performs human health and ecological risk assessments and undertakes groundwater solute transport assessments, including modelling. He is also an expert in acid sulfate soil identification, assessment, remediation and management, and provides independent expert witness services for legal proceedings, including court appearances. Some of you might recall Mark did a previous webinar on acid sulfate soil management, which was excellent. You can find that on our website under webinars. There's a recording of it there. So it's great to have Mark back again, and Mark, we really appreciate your passion for sharing your knowledge. Before we let Mark take the reins, we love your questions. And to raise a question, please use the Q&A button at the top of your screen, and we will read those questions out at the end of the presentation, and Mark and myself will endeavour to answer them. Why does HydroTerra do these webinars? Well, it's always good fun catching up with friends and colleagues, I suppose, but it's also great to share knowledge, facilitate education, and we like to take an industry leadership position here at HydroTerra. Right, without further ado, I'll hand over to you, Mark.
Thank you, Richard, and thanks for the introduction, and hello to everyone out there, and welcome back, presumably, to quite a few of you from the part one of this presentation. And as Richard mentioned, the initial part of today's presentation will just be a bit of a recap on part one, which did focus more on the soil side of the assessment process, or the tiered assessment process. So we'll just relatively quickly run through the slides from last time, just highlighting a couple of key points that I wanted to reiterate. This time around, the primary one being that the way that we do contaminated land assessment in Australia is governed by a national approach that we have, the assessment of site contamination NEPM, There are two major schedules. Schedule A, which details the process that we follow, which is a tiered approach. The key message here is that if you do a tier 1 assessment and you have exceedances of tier 1 criteria, then you move on to a tier 2 or tier 3 level of assessment. I think if you move on to slide 10, I think, Richard, the next one. So this particular slide just reiterates what I've just mentioned, that if you have exceedances of your tier 1 values, then that doesn't mean that you need to remediate, notify the regulator or various other things. It means you need to move on to a tier 2 or tier 3 assessment. These tables here just provide some examples of some of the tier 1 numbers that we use. So obviously, if we're doing a tier 1 assessment and all of our results, for all of our data comply with the tier 1 values, that's great. We can sign off on the side and move on. But if we have any exceedances, then we need to put in a bit more effort to explain or determine whether or not that's a concern through the tier 2 and tier 3 process. I think the next key slide, Richard, is 14. Yeah, so one of the key components of a tier 1 site, detailed site assessment is development of your conceptual site model. The key message here to reiterate is just that as part of your data collection for a tier 1 assessment, you need to do more than just test for concentrations of your chemicals of concern. You need to determine the concentrations of various other chemicals that will assist you in your tier 2 and tier 3 process if required. A key component of that is if you're installing groundwater monitoring bores, at the time of installation, you need to collect a sample of the matrix you're drilling into and installing into. And then for groundwater sample analysis, for any samples of groundwater you collect, you need to analyze for additional parameters other than your chemicals of potential concern. That's a key message. Next slide, Richard.
So, sorry, Mark, just on the moment that someone needs to start thinking more broadly from just collecting, maybe the contaminants to move to this broader in-depth, that's once you've moved through to is it tier 3, or how does that, what's the actual trigger to decide that?
Yeah, the key message here is that you need to really be thinking about this right from the beginning of the process. So right in the tier 1 step, or even planning for the tier 1 step, which is where you produce your sampling analysis quality plan, or SAQP. So you need to be envisaging the potential that you will be required to move on to a tier 2 or tier 3 assessment whilst you're undertaking the tier 1 assessment. And the best example of that is groundwater bore installation. If the only opportunity you have to collect a sample, a solid matrix sample from the aquifer material, is at the time of drilling and installing the groundwater bore, which is at the tier 1 stage. So you need to be collecting samples at that point in time to allow for the possibility that you will have to analyze those samples in the future as part of a tier 2 or a tier 3 assessment.
Okay. And can they keep those samples for quite a long time for the matrix, or is it sort of a bit time dependent?
It'll obviously be subject to holding times for analysis of chemicals of concern. However, the other parameters that we need to analyze for, so if you go to the next slide, it'll explain that. So the important parameters, depending on whether we're looking at organic or inorganic chemicals of concern, the important parameters we need to analyze the aquifer matrix for are primarily organic carbon content and cation exchange capacity. So the holding times on those parameters are longer than it is for certain chemicals of concern, particularly volatile ones. So yeah, you can collect your sample and wait some time before you analyze it if needs be.
You think in the industry at the moment, like it's obviously competitive to win the work, right? So I'm just wondering when people scope out their first assessment, is would you say the industry's following this at the moment or
Uh,
partially? Or,
yeah, partially or not really. I think the important point to understand about something like this example we've got on the screen is it actually costs you no more money at all. All you've got to do is make sure you collect a sample of that aquifer matrix when the drill rig's providing you samples from it. There's no laboratory analysis associated with it until you determine that you do have some contamination that you need to quantify the potential migration of. And part of that is, getting organic carbon and cation exchange capacity data for the matrix, and possibly also analysing the chemicals of concern themselves.
yeah. Okay. I'll move to slide 17.
Yeah. Yeah, so this slide just reiterates the importance of collecting this additional groundwater data that will enable you to make an assessment or to be able to quantify the extent or otherwise of natural attenuation processes that are occurring in groundwater, along the flow path and along the plume migration pathway. So it's the indigenous microbes present in the aquifer matrix that are going to assist in the breakdown of your chemical contamination in groundwater, and they're going to be utilizing certain chemicals in the groundwater, such as sulfate and nitrate, and be producing products of their respiration process as well, such as iron and manganese. So determining the concentrations of these parameters along a flow path within a plume is critical to being able to demonstrate and to understand plume dynamics and what the potential risk to the relevant receptors that these plumes are migrating towards is.
That sequence represent a typical journey, does it, of hydrocarbon degradation? So in a oxygen reduced environment. So
Yes, that's exactly right. So obviously the indigenous microbes will, to assist in them breaking down the hydrocarbons or other organic compounds that are present in the plume, will utilize dissolved oxygen first of all, because that's the most readily available for them. And after they've used that up, they'll utilize the nitrate because that's the next most readily available. Then they'll utilize iron and manganese oxides in the aquifer matrix and produce, iron 2 and manganese as well as part of that respiration process. After that, they'll utilize any sulfate in groundwater. It takes more effort to remove the oxygen from the sulfate molecule than it does from nitrate. So, they'll only use that preferentially if they've utilized all of the nitrate. And then, yeah, the final process that they'll utilize is the methanogenesis, or utilize the methanogenesis process. So yeah, it is a sequence.
yeah. So if you've got different inputs of more oxygen rich water, like a leaking stormwater pipe or something halfway along that journey, then the story could get a bit complex. Yeah.
It could. I mean, it could. Ironically, some of these. So another example would be that if you've got nitrate-rich groundwater, and we know that in our urban areas, for example, quite often there is quite a bit of nitrate in groundwater from leaking sewers and other potential sources. So, you know, it's slightly ironic that occurrence can actually assist the indigenous microbes in breaking down a hydrocarbon plume, for example.
Thanks. All right, I'll move on to the new slides. All right.
So as Richard mentioned in the introduction, today we'll concentrate a little bit more on uh, on the approach to quantifying the potential effects of migration of dissolved chemicals in groundwater, and how we can quantify that, and as part of that process, you know, assess the risks to potential receptors from groundwater migration. So one of the important pieces of information you need to determine to allow you to do this is to work out what we, you know, or utilize what we call the distribution coefficient. So that's the way that certain chemicals, dissolved chemicals in groundwater, behave in relation to components of the matrix. So we're primarily looking at, you know, the organic carbon content of groundwater, the clay content of groundwater, the cation exchange capacity of the matrix, sorry, that the groundwater is migrating through, which is essentially quantifying the ability that the matrix has to interact with these chemicals that are dissolved in the groundwater, you know, as the groundwater migrates through the pore spaces in the lithology. So this particular example on the screen is providing an equation that allows you to determine the distribution coefficient for certain chemicals, and the examples we've got in the table here are for zinc, copper, and manganese dissolved in groundwater based on a number of inputs. So if we can determine parameters of the aquifer matrix, such as clay content, organic carbon content, cation exchange capacity, and then combine that with knowledge of the chemistry of the groundwater itself. So in this particular example, utilizing this equation, if we know the concentration of calcium in groundwater, and then we obviously know its valency as well, and the valency of the chemicals of concern we're looking at, we can use the equation here to determine the distribution coefficient, or KD. So this particular example shows that for zinc, copper, and manganese, we use the parameters for this particular matrix to come up with KD values of 0.6, 0.4, and 0.3, respectively. Then we can use that distribution coefficient value to further estimate what we term the retardation coefficient, which is represented here by R. So that's just combining the distribution coefficient with the physical parameters of the matrix, so the bulk density and effective porosity, or bulk porosity of the matrix, combined with the distribution coefficient to determine the retardation factor, or R. So once again, for the example of zinc, copper, and manganese here, we've got retardation factors that are calculated of 4, 3, and 2.7. So what that means is that we're predicting that for these three dissolved chemicals, dissolved metals, that they will be migrating, you know, 4, 3, and 2.7 times slower than what the groundwater is migrating. So that's a really powerful tool to be able to allow you to estimate how long it may take these chemicals to reach a certain receptor, if you have been able to identify it and you know how far it is from the source of your contamination.
I guess just thinking about the physical flow of the groundwater, and how long it's got to interact with your matrix. Do you typically find that this does evolve to reflect those relative rates? Or do you think the physical factors of how groundwater moves makes a significant difference to that?
Yeah, that's a good question. I mean, the rate of groundwater migration is obviously dependent on the physical components of the lithology, and in a broad sense, you know, if you've got a clay dominated lithology compared to a sand or gravel, then groundwater is going to migrate, or is likely to migrate a lot slower through the clay, simply because of the small size of the pore spaces. So that is a factor. However, it's probably more that the scale of groundwater migration, even through sands and gravels, is still, you know, relatively slow. So it provides time for interaction between the dissolved and solid phases of the matrix.
I move to the next.
Yeah. Thank you. So this slide is providing exactly the same information as the previous slide, except that this is giving you the calculation required to estimate retardation of organic compounds. So for organic compound retardation, we're simply using organic carbon as our parameter, because of the much more significant interaction of organic carbon with organic compounds in a matrix compared to other components of the matrix. So the distribution for the distribution coefficient for organic compounds is simply, you know, the multiplication of the organic carbon or organic matter distribution coefficient with the fraction of organic carbon that you measure in the matrix, but by analyzing it for organic carbon content. The organic carbon distribution coefficient, or KOC, is a value that you obtain from the literature. So those values, so for example, that are listed in this table for a series of chlorinated aliphatic compounds, PCE, TCE, etc. The KOC, or organic carbon distribution coefficient, is a literature determined value. And then you simply multiply that value by the fraction of organic carbon that you measure in your sample to get the distribution coefficient, or KD. So this particular example here, we've got a fraction of organic carbon, you can see in the notes below the table, of 0.0003, which equates to 0.3% organic carbon was measured in this particular sample. So you make that calculation, come up with your distribution coefficient, or KD, and then the same as for inorganic compounds, you then use your retardation, comparing the bulk density and the porosity, and then multiplying by the distribution coefficient to come up with your retardation value there. So you can see in this example that, you know, for a range of organic compounds, whilst they're chemically related, they're all chlorinated ethenes. They do have a wide range of KOC values, with, you know, tetrachloroethylene, or PCE, TCE, and carbon tetrachloride being the most, you know, they have the most affinity with the solid phase, which results in them having the highest retardation factors that you calculate, which means that they will be the ones that move the slowest in groundwater. So what the rest of this table then shows is that you can use that value to calculate how much slower than groundwater the dissolved solutes will migrate. You know, so in this particular example, you can see those values there, and then you can further combine that with a if you also know the degradation half-life of these compounds, so they will naturally degrade in the environment anyway. You can utilize that information as well. One of the important things to understand in using these equations is, you know, the importance of having actual data from the matrix itself. So we've talked about the criticality of having organic carbon data from the matrix. You know, other data that would obviously be really valuable here would be bulk density and porosity data. The other point that I want to make here too is that, you know, with all of these parameters, there's a level of uncertainty. So it's important to, you know, whilst you're calculating a single value, it's also important to consider the possible ranges as well. So that you'll see that this table has provided, as well as providing a single value for some of these parameters, and in particular the retardation factor, and then the velocity of migration of these solutes in groundwater. You can also present your data in a range, and the range here is determined by the uncertainty associated with the effective porosity values.
So the half-life, that's someone's estimate of how long it's going to hang around, right? Or it's
Exactly.
degraded.
Yeah. So in this table, it's important to understand that the KOC, or the distribution coefficient values, and the half-life values are literature values. They're obtained from the literature.
So I suppose I'm just wondering the assumptions on the half-life. Like,
Yes.
is it assuming it's an oxygenated environment or a...
Yeah, that's extremely good question. So you'll see that in the table notes at the bottom of this table, it cites some references for determination of the half-life, and those different papers. One of the examples cited there is for oxygenated groundwater, and another is for groundwater under reducing conditions. So obviously, you know, another parameter you'll be measuring as part of your sample collection for groundwater is the redox state of the groundwater. So, you know, that collection of that data will enable you to determine what's the best literature values to apply to your particular scenario.
This is all pretty complicated stuff, Mark. Shall I
Yeah.
move to the next slide, or you want to start this?
Well, just the final point I'll make in response to what you've just said is you're entirely correct. And obviously this is a very, you know, complicated process. However, all I'm trying to get the message across today is that, you know, whilst it is a complicated process, it's also a stepwise process that's well described in our guidelines and the literature. And it's just a matter of following these processes and making sure you've got all of the checks and balances in place. And, you know, the important thing I think to understand is that, you know, really, if you are investigating a contamination plume that is migrating towards a receptor, then this is the type of effort that is required to determine the risk associated with that.
So maybe just ask one more question. The meters per year, so VS is...
That's the
That's
velocity
velocity.
of the solute, so the chemicals, the dissolved chemicals there.
Oh, okay. The solute.
Yeah, yeah. So you'll see in note 2 in the bottom of this table, it provides, so the attenuation rate of groundwater has been determined. So obviously, you know, the rate of migration of the solutes is compared to that rate of migration of the groundwater via the retardation factor.
Okay. Yeah, I think that makes sense. I'll move to the next slide.
Yes. So after that very complicated or complex introduction, these next few slides are going back to the basics, to the actual collection of the groundwater physical data that you need to do to help you to determine things like parameters like hydraulic gradient, groundwater flow direction and groundwater migration rates. So, the first piece of information you need to collect as part of assessing groundwater data from a series of groundwater monitoring bores is to be able to measure the hydraulic head or the static water level in each of those bores, compare them to a common datum, and then determine groundwater flow direction and the gradient at which that groundwater is migrating. So this example here just provides all of the physical data that you can collect to assist you to do this. So you've got a series of monitoring bores. Obviously, their spatial position, so their eastings and northings is critical to be able to plot them on a map. You need to have a surveyed height of your reference point, whether that's the top of your PVC casing or the top of the gaddock cover. The total depth of your bore is also critical to know. And then your gauging measurements, so your measurement of static water level, can then be compared to the common datum to allow you to calculate a relative height of groundwater, which can then be compared to other locations at the same sampling point, and it can also be compared to the same location over time. So what you can see here on the bottom right-hand of this screen is the hydrograph that has been generated from this data in the spreadsheet, which shows you a number of things. It first of all shows you the consistency of the groundwater levels over time compared to each other. And it also shows you the height of the groundwater at each sampling location, compared to your other locations at a point in time, which then allows you to determine groundwater flow direction. It also enables you to compare the levels to other features that are associated with your site. So this particular example, we were particularly interested about the potential ingress of groundwater into a basement. So you can see the line there that gives the relative height of the basement slab, concrete slab. And so you can see that some of the groundwater locations have got a head level that's below the level of the slab, but some other ones are above the level of the slab. So that will, obviously provide you valuable information about, how groundwater at different locations will behave with reference to something like a basement structure. Now, another important hydraulic parameter that you can collect as part of your groundwater assessment is slug test data. So that's simply where you change the static level of groundwater in your bore, and then measure the rate that change migrates back to the static level, and that measurement allows you to estimate hydraulic conductivity, or K, of the groundwater unit that you're sampling or assessing. So that's this is really valuable data that can be collected relatively simply. You obviously in most instances will need a data logger, instrumentation that allows you to collect head readings, on a sort of per second to per minute basis, and that data can then be interpreted to come up with estimates of hydraulic conductivity. You can see in the example provided here, the plot on the left-hand side is simply the data from a data logger that was placed in a bore. So the straight line component of this data is the static water level, and the peaks and the increases above and below the line are where a slug has been introduced to the water that's increased the water level, and then it's retreated back to static. And then once the slug is removed, the opposite occurs. So the level comes back up to static as well. So you get two tests for every time you introduce the slug to the water and change the level, and then once static has been achieved, you then remove the slug, and the same test is repeated again. And so it's that repeatability, obviously increases the value of the data. If you could just go back to the previous slide, Richard, momentarily. Yeah, so the right-hand side of this particular slide provides the raw data that is collected, and then it's interpreted to be able to calculate the relative head changes over time that can then be interpreted using a couple of different methods that we'll detail in the subsequent slides to estimate your K values. The other important thing to understand about this data is that the accuracy of it, it's obviously a relatively rudimentary test. So you're really only aiming to estimate your hydraulic conductivity values within an order of magnitude. So is the hydraulic conductivity of my unit 1.1 or 10 meters a day? But nonetheless, it's very valuable information. You can go to
The sort of rule of thumb of how many slug tests people should take on a site.
Yeah, the rule of thumb is as many as possible, at least one in each individual unit that you've got bores installed into. So I guess if you take a standard example where all of your bores on a particular site are installed into the same water-bearing unit, then at least one test would be great. And a test on each of the bores that you install would be fantastic. The pragmatic result is probably somewhere in between. But yeah, the more the better. But just one test is obviously infinitely better than no tests.
Just maybe for some of the people who may not have done slug tests before, slugs typically just a PVC tube that's maybe filled with sand and capped each end, and you drop it into the well, and it instantaneously lifts that water level up.
Yep.
And then you've got a data logging device that you can set at a certain frequency of measurement, and you collect that time series data as the water level equilibrates back to its original level. And then you can do the reverse thing where you pull the slug out and it instantaneously drops the water level, and you measure the recovery side of things. And then there's various software packages these days that you can just plug that data into.
Yes. Yeah, that's an excellent description. And so that the plot on the left-hand side there shows exactly what Richard has just described. It's just a slug's been placed into the bore, displaced the water level, it's returned to static, the slug's been removed. The same thing has happened, and this has been repeated 3 times in this particular example. Yeah, and the data that's presented in the middle of this slide, you probably can't read it because it's a bit small, but that data was collected. There was a data point collected every second. So we were able to show the change in head second by second. And it's the relative change from static, which is what we're really interested in. And when we plot this data on semi-log plots, which there are examples of on the right-hand side of this slide, then your aim is to get near enough to a straight line that you can determine the slope of that line to help you calculate your K value.
Can you use AI to do it all now, Mark? If you've got the data logger file, can you just dial it up and say, do an analysis? Or Still
I'm
got
sure.
to plug it
I'm
in.
sure you can. I'm sure you can. One point I would say about that, and also, you correctly mentioned that there's plenty of software packages out there to analyze this data. I find that analyzing the data manually by, just in a spreadsheet is also important, because it provides a cross check against your software package calculated values as well. Like you shouldn't just blindly trust the outputs of a software package. You need to think about what the data it's providing you as well. And I find doing some manual measurements in a spreadsheet, Excel spreadsheet, is a pretty quick and effective way to calculate these values as well.
All right, move to the next slide.
Yes. So this slide shows another method of interpretation, which, if you have the right conditions, is a pretty powerful tool. So this is the Cooper method, which you can only use this method if you've got a fully submerged screen. So what that means is that the intake screen of your groundwater monitoring bore is completely below the water table, so is completely saturated. But if that is the case, then you can use this method. It's a curve fitting method to help you, in addition to determining hydraulic conductivity, or K. It will also determine specific storage, which, if you know the thickness of your water bearing unit, or the length of you can just use the length of your screen as well. It can help you to calculate effective porosity, which can be directly related to the storativity calculation that you're making can be directly related to effective porosity. So that's an important term in groundwater. So this can be a really good method for also getting that piece of additional information.
So the outputs you get from the slug test is hydraulic conductivity and
And using this Cooper method, you can also get effective porosity, or storativity is another way that it's termed as well. So here's an example of just presenting the output of the data, and also assisting you in this calculation. So this is just an Excel or an output in Excel, which has got all of the input parameters, the physical input parameters on the left-hand side there. And then the K value is calculated using a couple of different methods. The main, or the most common methods that are used for calculating these parameters are the Hvoslev and the Bauer-Rice methods. So by using another number of different methods of interpretation, it just increases the rigor of your estimates, if you like, particularly if you can get your calculations to match between different methods. So once again, it's wherever possible, repeating your tests as much as you can, using as many locations as you can afford to under your budget, and then interpreting the data using as many different relevant methods as well. Just provides you really valuable information and a level of confidence in the output of your data. You can see also in this spreadsheet that if you know the hydraulic gradient and effective porosity of your lithology, then you can use Darcy's law to calculate the attenuation velocity as well, based on your hydraulic conductivity value. So this example here, you can see that it's a pretty low yielding unit, in that the hydraulic conductivity is less than 0.1 meters per day, which is quite low, and the resulting estimated attenuation velocity is therefore also very low. An average of 2.5 meters a year migration of groundwater in this example. So once you've collected all of your physical data, you've determined your hydraulic gradients, groundwater flow direction, you've estimated your physical parameters to the degree possible, so your hydraulic conductivity, perhaps your effective porosity if you can, and you've got your dissolved chemical data from your groundwater sampling for your chemicals of concern, then you can undertake, solute transport assessment. So you can use your calculated retardation coefficient values that you've calculated and we've been through to undertake a solute transport assessment. This is an analytical approach, done in an Excel spreadsheet. So there's a few key things that you need to understand about your plume, whether it's an ongoing source or continuous source plume, or whether it's a plume that the source has been removed from, and so therefore it's termed an instantaneous point source plume. So all you need to model is how what remains of the plume will behave in the future. So the parameters that you're trying to estimate are listed down the left-hand side of this this slide. So you've obviously determined the flow direction of the groundwater and the rate at which it's advecting, so the rate at which groundwater is migrating. Then you can add to that information the rate that quantify the rate that dispersion is occurring, which is effectively the dilution of these dissolved chemicals in groundwater as they migrate along a groundwater pathway. Then in addition to that, you can add the absorption or retardation term into your equation. And finally, you can add in the decay term, or this is where we talked about earlier, the half-life of the particular compounds that you're modeling. So once you've, incorporated all of those parameters into your model, you can see that the aim is to come up with a more realistic assumption of how that groundwater plume is going to behave with distance away from the source, whether that source is ongoing or whether it's a prior source that's been removed and is no longer there. So you can see that this is a very powerful tool, because it allows you to conclude things like, well, the rate of migration of these chemicals in groundwater is going to be significantly slower than the groundwater itself. So it's only going to go a certain distance rather than the same distance that groundwater itself is going to migrate in that time, and that the concentrations in the plume itself of these chemicals will also be declining over time due to these processes that we've been able to quantify.
So the common application of empowered with that knowledge would be to be looking at, say, the boundary of a site, which might be, say, that bottom arrow with X on it. So let's say it's a kilometre away, and you're using this to say whether or not there's going to be a concentration that's exceeding some acceptable criteria at that distance.
That's exactly right. Yeah. So a site boundary is a good example. Another example would be a groundwater bore that's used for some purpose, so a water supply bore or something like that. That's downgrading of your site and your plume. And then another common example would be a surface water body that is a receiving body for groundwater. So groundwater is discharging into a creek, for example. So that the distance from your plume to that creek, would be another example of where this scenario is relevant.
You were talking about the slug test and the uncertainties and saying, well, it's an order of magnitude, error, if you like.
Yep.
How does that play out in terms of that bottom picture there? Is that how do you take into account that broad span of that?
Yes. So any solute transport assessment, any modelling exercise that you undertake needs to consider as part of the assessment uncertainty, and also, you also need to do a sensitivity assessment, which is to determine which particular parameters that you're using in your model are more sensitive to changes that will result in a significant change in the estimated migration distance or resulting concentration of your chemicals. Yeah, so you need to consider uncertainty and sensitivity. So one of the ways that you do that is by considering the realistic ranges of all of these parameters. So rather than coming up with one number, you come up with an estimated best estimate, but also a potential range. And then the other important tool, if you like, or function, if it's possible, which we will deal with on the next slide, is being able to calibrate these estimates using actual data. So what we've got here in this output, so this is a solute transport modeling output. In the plot at the bottom of the page there, it's got the estimated concentration of the particular chemical. So in this example, we've got PCE, or tetrachloroethylene, concentrations along a plume migration pathway. So you can see distance down the bottom of the plot is distance from the source. So you can see that it is estimated that, or predicted, the predicted concentration of PCE in this plume starts out at about 1 milligram per litre. And by the time that you've got a distance of 90 meters from the source, it's essentially predicting that the concentration won't be detectable. Obviously, we're dealing with a log scale in terms of concentration here. Now, what we've got in this example also is some actual data measurement points from various monitoring bores that are placed along the plume pathway. And so what you can see here in this example is that we're able to show that the predicted concentrations, which are the blue points, correlate, fairly well with the actual measurement points that we have along the pathway. So there's once again there's a lot of information provided in this spreadsheet, including the outputs. So obviously the model output will enable you to predict the concentration of the particular chemical, PCE in this example, at any distance down gradient of your source. And obviously if you've got an identified receptor or a site boundary, you'll be able to predict what the concentration will be at a certain time in the future at that point. So I guess a point I would reiterate here is just that this outcome, which is a pretty powerful outcome, is all generated from just simply collecting this data as part of your site investigation process. And this allows you to make decisions, related to whether or not remediation is required, whether or not regulator notification is necessary. So it's, providing you with really powerful information to inform your process and provide certainty to your client, the property owner, as well, in terms of their obligations, or whether or not, and the extent of issues that they may have.
Typically request that someone undertakes numerical modeling, like in 2 or 3 dimensions when they're calculating this sort of things.
It's probably not typical, but it's definitely it's yet another tool that we have to increase the certainty of our predictions, really, is how I would describe it. So, in most instances, an analytical approach using slug tests to estimate hydraulic conductivity is an appropriate level of assessment. It's still a rigorous level of assessment, in particular if you're able to have a pretty comprehensive uncertainty and sensitivity assessment with good calibration, such as this example here. However, refining your hydraulic conductivity estimates through a numerical model is obviously, even better. So, I mentioned that slug tests will give you, your answer within an order of magnitude effectively. Then, one of the reasons for undertaking a numerical model will be to refine that estimate down to a more accurate value. I mean, we've talked just about slug tests here as well, but another way to get better groundwater physical data is to actually undertake a pumping test, where you're abstracting groundwater from a water-bearing unit and measuring the response in a observation well that's some distance away from the abstraction point, and that'll also provide you a much more accurate estimate of hydraulic conductivity. But obviously, that type of exercise is going to cost significantly more. So this is where the practicality of planning of the level of assessment that's necessary for the scale of the problem, and also the cost to fix the problem, all comes into play.
So when do you make a call? Like if you're reviewing something, I know as an auditor and they've just done slug tests, when would you make a call to move and say, oh, you really need to do a pump test here?
Yeah, well, that would be depending on the extent of the problem, and for example, the likely degree of remediation that's going to be necessary, because the other advantage of having, for example, a pumping test undertaken is that it's also going to assist you in designing a remediation system as well, if it's determined that you're going to need to be doing some remediation of groundwater as part of your assessment. So, I guess coming back to the tiered approach, that's the topic of this talk, is that the more data you can collect under the tier 1 part of your investigation, the more prepared you are to move on to a tier 2 assessment. And if we're using the example where an auditor is involved, and in particular if the auditor has been engaged since the commencement of the investigation process, then interaction between the auditor and the assessor can ensure that, at the very least, slug tests are undertaken as part of this work. And then if significant contamination in groundwater is identified, then a pretty quick decision can be made at the end of the tier 1 process and commencement of the tier 2 process as to what other data needs to be collected.
Okay, move on to the next slide.
So the following slides will just deal with the interpretation of the chemical groundwater data. So here's an example of a spreadsheet that's just used to compile data, which is the groundwater inorganic ionic chemistry data. So in this spreadsheet, even though there's a lot of rows and numbers here, it's only the cells highlighted yellow, which are the actual input cells. So you'll see in the middle of the screen here, you've got your field pH and EC readings, and your laboratory determined pH and TDS, or total dissolved solid readings. So they're values that you collect either in the field and the lab, and then you can compare them to each other as a quality control check to make sure that they correlate with a reasonable degree of accuracy. And then over on the left-hand side of the spreadsheet, you've got your input parameters for each borehole and the date of sampling. So you've got your cations, or your positively charged ionic species, including nutrients. So that includes ammonia. And then you've got your negatively charged anions and nutrients. So your anions, as well as alkalinity is bicarbonate, nitrate, and phosphate, as well as fluoride. So those inputs enable you to make a number of calculations. So you can look at things like ionic ratios. You can, the bottom half of this spreadsheet converts all of that. So that data is in milligrams per litre. So the bottom half of the spreadsheet converts it all to milliequivalents per litre, so that you can then directly compare the total anion with total cation concentrations to make sure that you've got a balanced chemistry. So that's one of the powerful things about looking at groundwater inorganic chemistry, is because the inorganic chemistry, ionic chemistry, will have equilibrium concentrations of positively and negatively charged ions and species, then your charge balance, to be an accurate reflection of the groundwater chemistry, will balance out. So this spreadsheet provides a balance, or a check on the balance of that. It also allows you, in addition to the ionic ratios, to calculate various other parameters such as hardness, sodium adsorption ratios, various saturation and corrosion indices. This is all on a simple spreadsheet, just simply using ionic balance groundwater data. So an enormous amount of information can be gained simply by collecting that data as part of your assessment process. And laboratories should be able to analyze for all of these parameters for around $50 a sample, which is pretty cheap. So it's definitely value for money data.
We're running a little bit over time. Shall we move to the next one?
Yeah, so these subsequent slides are all outputs from that spreadsheet as well. So when you're looking at groundwater data, essentially what you want to do is one of two things. You either want to look at a series of locations, or all of the locations on your site, or all of your locations along a flow path at a point in time. So this particular example does exactly that. And what it allows you to do is identify areas of contamination along the flow path. And you can even, identify chemical processes that are occurring. So because this is a gasworks plume that contains elevated concentrations of ammonia in the groundwater, you can see that along the plume pathway, at some point, the indigenous microbes have been able to break down all of the nitrogen, but further on down the plume, more nitrogen comes into the system due to nitrification processes. So it's a powerful tool to enable you to demonstrate changes in chemistry along a flow path. Go to the next slide, Rich. And this is exactly the same data, but rather than looking at it in cross-section, we're now looking at it from a plan view, so from above. And you can see that the changes in groundwater inorganic chemistry reflect the migration of a plume. So in this case, a gasworks plume. So obviously, at this location, there's plumes of various organic compounds such as naphthalene, benzene, etc., that are migrating along the groundwater flow path, which is replicated through the groundwater chemistry. So this is another line of evidence to show the extent of the plume. So primarily what's happening here is the microbes that are extremely active within the plume center, producing a lot of carbon dioxide, which is converted to bicarbonate, whereas the background chemistry of this aquifer is sodium chloride. So it's a stark change in chemistry that you can plot to further demonstrate the extent of your plume. The next slide, Richard, is...
Before we do, just in terms of sort of deciding on whether you need to remediate or not, is you'd be looking at these various lines of evidence plus that modelling that you've done. So this is providing you with, I guess, more lines of evidence that the degradation, etc., that you've assumed in the modelling is actually occurring. Is that right?
That's exactly right. So You can see on this particular slide that there's a creek in the top right-hand corner there, or it's the northeastern corner. So this plume is migrating towards that creek. And so what all of our organic compound data, as well as this data, is predicting is that even though it's migrating towards the creek, the plume is going to degrade before it actually reaches the creek. So therefore, there's not a requirement to remediate this plume due to its potential to impact on the creek, because the modeling has shown us that the plume will actually not reach the creek. So in this particular example, it's a gasworks site, and we were undertaking the remediation of the on-site gasworks plume. So what we were able to demonstrate here is that by removal of the on-site source, the former tar wells on the gasworks site, we were able to therefore negate the requirement for remediation of off-site groundwater. So this particular data shows the situation where you're looking at one location over time, and you can see change in chemistry that is occurring at this one location as a result of various processes that are occurring. So this particular aquifer had urea injected into it to promote degradation of a hydrocarbon plume. And what we were able to do is track the behavior of the nitrogen that had been injected into the aquifer over time to demonstrate that various processes had occurred, which meant that not only were the hydrocarbons associated with the petroleum plume degraded, but also the nitrogen, which is also a potential pollutant, was degraded as well. So you can see that when urea was injected into the aquifer, there was a background chemistry, which is the blue line, the blue dots. The injection of the urea resulted in increase in ammonium concentrations in groundwater, which over time were the ammonium was nitrified, or the ammonium was utilized, but as a result of that, high levels of nitrate were subsequently created as part of the nitrification process. But then over time, that nitrate was also degraded and utilized by the microbes to break down the hydrocarbon plume. So at the end of the process, so the purple line on this plot, you were back to background groundwater chemistry similar to what you started with. And then the final slide, which is the next slide, Richard. So this is just one slide on soil vapor assessment. So I've talked today about groundwater assessment, but this is just also to let you know that you can essentially undertake the same process for looking at soil vapor concentrations of various volatile chemicals. And the reason that we can do this, so the reason that we can, model groundwater dissolved chemical concentrations so accurately is primarily because of, research that's been done in the past. So for groundwater, there's certain papers that allow us, or certain equations that have been calculated in past papers that will allow us to estimate the parameters. Likewise, in soil vapor, the Johnson and Edinger model approach, which this is a spreadsheet which is freely available from US EPA, is a spreadsheet utilizing the Johnson and Edinger parameters to enable us to estimate the risks to indoor air or to trenches or various other potential receptors from vapor migration as well. And it's just a simple spreadsheet which has a number of input parameters depending on the source of the volatile chemicals. This particular example uses groundwater, so it's a dissolved groundwater plume. The particular chemical we're looking at here is vinyl chloride. So you enter all of your parameters for your groundwater aquifer, the chemical parameters associated with vinyl chloride, the physical parameters associated with the soil profile between the groundwater and the indoor air environment. Inputting all of those parameters will then allow you to estimate the potential risk, to either indoor air or trench workers or any other receptor to vapor migration. So it's a really powerful tool that we have at our disposal, freely available.
So is that through the US EPA website? Is it? Do people get hold of that? Or
Yes, yeah, they can. It's called the JNE, or the Johnson and Enninger vapor intrusion modeling spreadsheet.
we might add that to our newsletter this month so people can get a link.
Yeah.
Mark, that was fantastic. We better move to questions. We had 2 early bird questions. What resources, official or unofficial, would you recommend when you're going through the process to ensure compliance with the guidelines?
Yes, that is a good question. I mean, in terms of resources, I think what I would recommend at a high level is, you need to be familiar with the NEPM, regardless of where you are in Australia. The NEPM is an extremely valuable resource. When we're talking about guidelines, people would know that a lot of our legislation and guidance in Australia is state-based. So depending on what state you're in, it's really important also to understand what the state-based guidelines are that you need to refer to. Pretty much all of the state EPAs have these resources available on their websites these days. So, a quick, on the websites I'm most familiar with are those for New South Wales EPA and EPA Victoria, and both of those, if you just go onto those websites and type in guidelines, it will take you straight to the relevant guidelines sections for those state-based EPAs. So that's a really powerful tool for you. And it's also, probably my final point for this question is, it's also important to understand that these state-based guidelines, there's no reason why they're not relevant in other states as well. So just one example is that the New South Wales EPA ground gas guidelines are really good. So obviously there's no reason why you can't apply them in other jurisdictions. And likewise, most of us would know that in the WA guidelines for assessing asbestos in soil are also really good. So there's no reason why you can't use them elsewhere as well.
An auditor, are you allowed to sort of give to an assessor sort of effectively a bit of a guidance checklist and say, look, make sure you're following these particular guidance documents?
Yes, and most of any of those type of recommendations, it's all contextual. Yeah, so every audit I do is on obviously a site specific basis. So whatever particular issues come up on an individual site, then if certain guidelines are relevant to the certain chemicals of concern that have been identified, or the certain lithology encountered, those sort of things, that definitely will be recommending particular guidance to practitioners. Yeah.
All right, next question. Who pays for investigation or remediation if contamination from USTs, old USTs, are found a bit over a neighbouring boundary? A bit, like a little bit?
Another good question. Yeah, I mean, most state-based legislation says that the polluter pays for, not only cleanup but also investigation of contamination. So in this particular example, you would imagine it would be pretty easy to identify who the polluter is, or who the source of the owner of the infrastructure is. So I would, generally say it's the owner, or the source, or the polluter that pays. Now sometimes, getting that to happen may have to be via legal pathway. But yeah, I would think in a pretty clear-cut situation where it's obvious what the source is and who the owner of that is, that should be pretty straightforward.
I remember many moons ago when I was auditing, there was a site where half of the underground storage tank was under the footpath and half was under the building, and I guess neither the council, who probably owned the footpath effectively, or the owner of the building had been responsible for the original placement of that underground storage tank. It was an old roadside Bowser storage tank. So who's the polluter then, Mark? It's halfway between two things. So,
Well,
I,
it sounds like it could have been a third party.
yeah, I don't know. I gave that audit back to Roger Parker when I left Golders, so we'll have to ask him. Just onto a couple of questions raised during the talk. So, question from David Detrick. G'day, David. It's confusing that tier one means initial and potentially more detailed assessment. I use continue to use phase 1, 2, 3 for initial, detailed, and rehab phases of site contamination. Is it? Does that make sense to you, Mark?
I think so. I mean, it is quite common for phase or stage to be used to demarcate certain components of an overall investigation process. I mean, I guess what I just keep coming back to is Schedule A of the NEPM. I just find that a really valuable, the flowchart there, a really valuable tool just to remind you, of the process. And obviously within each of those components of the pathway, so the PSI, the tier 1 PSI, the tier 1 DSI, and then the tier 2 or 3 site-specific components, within each of those you can have various phases or stages. And I agree that it often helps to break it down a bit more than what it is in Schedule A, but yeah, Schedule A just provides a really good overall framework, I think.
Next question from David. You should always log a bore and collect samples at a CS contaminated site. I guess that's not really a question, but a
Yeah,
statement.
I
Would you
think
agree with that?
I think what David's saying there is that yes, absolutely. Like I've concentrated today on collecting samples from the aquifer matrix, but yeah, standard soil sampling, when you're collecting soil samples, you should absolutely be collecting samples from every lithology that you encounter, regardless of whether you're planning to get those samples analysed or not. Yes.
People tend to log things in different ways depending on who taught them. Has the world settled on a classification standard?
I don't think it has. However, an important thing to understand is that there is an important difference between scientific logging for contaminated site assessment or for looking at the chemistry and physics of soil for a contaminated site assessment as compared to a geotechnical assessment. I think that's an important distinction to draw. Yeah.
All right, next question is from Isabel Simonson. How does the pH affect the distribution coefficient? This is on slide 26. Both the surface charge of the soil particles and the water environment of the metal ions should depend on water pH.
Yes, that's correct. So pH of the matrix or of the solid phase is not going to be overly informative to you in terms of estimating migration potential of various chemicals, but yeah, absolutely. The pH of the water will be critical for dissolved metals whose solubility is, in some instances, entirely dependent on pH. So yeah, the pH of the water is really important. I mean, that's a quick example that if you've got a dissolved metals plume in your groundwater, then a simple remediation strategy is to change the pH, raise the pH. And if you can manage to do that, then your metals are just going to absorb to the matrix.
That's probably another webinar topic in itself. Next question. David's back again. What samples would you recommend? So this was following on from the soil logging comment. What samples would you recommend? So
So I'm going to guess that what he might be referring to is soil sample analysis for analysis other than your chemicals of concern, which is probably detailed on slide 14 of the talk from last time. Which is essentially your organic carbon cation exchange capacity metals other than your standard 8 like iron and manganese, pH, EC, and then also any physical parameters, so particle size distribution can also be a valuable analytical tool as well.
I guess you might also be referring to, like, do you take a sample from every saturated lithology or
Yeah, absolutely. So if your investigation has encountered more than one saturated unit, then yeah, you would need to collect samples from each of those for sure.
David, a little bit more detail on the next question, please. All right. Karen Hilton, when considering migration of contamination, does that mean you also need to understand how long the contaminants have been in the groundwater?
Yes, absolutely, and that's a good question. And in particular, if you're trying to demonstrate that the source is no longer there, so because if you're using what we call the instantaneous point source model, so one of the parameters or one of the components of the contamination that you will need to try and estimate is the mass of the plume. So the time that the plume has been in the ground is really important. It's also really important as part of your calibration as well, because obviously as part of your calibration, you're predicting how far a plume migrates from a source over time. So the starting time is really important. So often your calibration process can actually assist with you determining when the plume commenced, because that'll fit in with your calibration.
So your analysis when you were looking at the milli equivalents and looking at the iron balance, right? Anion cation balance, is that a good indicator of whether a plume's stable or not?
Yes, it can be, in particular because one of the components of that cation anion balance is your alkalinity or bicarbonate, which is reflective of the degree of respiration that the microbes are doing in the plume to degrade that plume. So, really high levels of bicarbonate, as an example, can be a direct indicator of the fact that those microbes have managed to stabilize that plume. So they're, what you often see is a plume will be there, but it won't be migrating. And the reason for that will be that the microbes are able to, work on the periphery of the plume to degrade the organic compounds that are dissolved in groundwater at the same rate that what those compounds are migrating in the groundwater. So effectively, that's what a stable plume is that, even though the groundwater itself is still migrating, the plume is stable and stationary, if you like, because the microbes have been able to reach some sort of equilibrium where they've stopped the plume itself from moving further down gradient.
All right, Rod Harwood, slide 29. Slug testing can also be used with simply a slug of water added or removed, not necessarily with a slug of sand.
Absolutely. So one thing I didn't mention is that particularly if you've got a lower yielding lithology, so you're dealing with an aquitard, which often we are. So a couple of things, you can do these tests just by adding water to the bore and measuring the rate that it, you know, recharges back to static, and alternatively you can pump your bore dry and then measure the rate that the water recovers in your bore. And oftentimes, if it's a slow rate of recovery, you can do hand measurements rather than having to use a data logger. So yeah, absolutely.
Rules of tipping water into a well. If it's potable water, that's okay. You don't need to worry.
Well,
Chuck that
yeah,
in.
clearly, if you're going to do that, there are some things you do need to consider before you do so. But there are circumstances where that's an appropriate thing to do.
Yeah. Um, David says sorry. So that's good, David. Thanks, mate. I appreciate the questions. And Mark, we've got to the end of the webinar. Thank you very much. I think that definitely warranted the sequel, and it was really very interesting. So many thanks for your contribution. It was great.
Pleasure, Richard, and thank you for the opportunity and for putting these seminars on.
All right. Thanks, everybody.